No, I met Sola through the Pittsburgh chapter of Jack and Jill, so I know he is a family-first gentleman. And in talking to him at that event, I was amazed at the stories that he told, not false stories, right? All true stories, but the passion at which he spoke about not just nuclear energy, but what it meant to Pittsburgh and to the world. And it was enthralling. I lost track of time, frankly, Sola, as we talked. And in that, it really struck me as we were planning for this event, early stages of that, and I thought, wow, what a great speaker, and what a great opportunity to share his message with you and for you to hear his message. I think you're going to be very impressed with that. But first, I do need to set the stage for who you're about to hear from. Dr. Sola Talabi came to Pittsburgh in 1997 to study engineering, and he's earned it. This list here exceeds anything that I've seen. A Bachelor of Science in Mechanical Engineering from the University of Pittsburgh, Master of Science in Mechanical Engineering, an MBA and a PhD in Engineering from Carnegie Mellon University, and is also a certified risk management professional. He serves on the National Academy of Sciences Engineering and Medicine Committee on Advanced Nuclear Power Plants. He serves on the University of Pittsburgh's Industrial Engineering Safety Engineering Committee, and he serves on the World Health Mission Board. He was formerly a member of the UPMC Diversity Board and the Urban Pathways Charter School Board. Sola has over 21 years of experience in designing nuclear power plants. He is a world-recognized expert on advanced nuclear power plants and owns the design for the only existing 1-to-1 scale small modular reactor experimental facility, which is in his research lab here in Pittsburgh. Sola advises the International Atomic Energy Agency on safety standards. He is a leading voice for the demilitarization of the nuclear power plants in Ukraine. Sola has authored over 30 journal and peer-reviewed publications on advanced nuclear reactor design, and he's currently adjunct professor of nuclear engineering at the University of Michigan and the University of Pittsburgh. He has also designed several devices to improve public safety, including a device to prevent crowd stampedes, a device to detect and deter mass shooters, and a device to increase safety of both police and motorists during traffic stops. Sola is currently the president of Pittsburgh-Technical Consulting. So I cannot wait to take my seat and take my notes. Please give a warm welcome to Dr. Sola Talabi.
Okay. All right.
Thank you, Matt. Yeah, so Matt and I met about
6 weeks ago.
and I was just as excited
speaking with him, and so I have quite a few events that I'm also going to, possibly have you come speak at, because Matt had a lot of very interesting stories and interesting perspectives, and when he and I met, it was like, we've known each other forever, and just really hit it off. So thank you for this great honor. Clicker.
So the time now is probably about
Maybe about 10 after 11.
and,
In about an hour from now, when we're done with this session,
a lot of people around the world now who are
a lot of people around the world who are
thousands of
people are alive now, but by the time we're done in about an hour, they'll be dead. A lot of them will die because of issues related to global warming, but most of them will die because of issues related to global energy poverty. My brother is one of those people. He lived in Pittsburgh for about 20 years, went to Nigeria got there on a Sunday, and by Wednesday he was dead. He had an accident, was taken to several hospitals, and none of them had blood because they didn't have electricity to refrigerate the blood, and so he died.
All right, old school. So a lot of the challenges we have around the world are related to energy security. You can think about climate. If we don't address climate change with clean solutions, will further exacerbate the climate change issue. For economic growth, developing countries certainly need energy to power plants. Healthcare requires energy. And even a lot of the military conflicts that we continue to have all have military undertones. Global warming and global energy poverty are inextricably tied. We also see that relationship in the aspect of vulnerability, where the countries that have contributed the most to greenhouse gases are those that are least vulnerable, while those who have the ones who have contributed the least are the ones that are most vulnerable, while those that have contributed significantly are the least vulnerable. Also, and this is all sort of setting the stage for the work that I do and the topic that I'm going to talk about regarding nuclear power. But we also see that we're going to have this tremendous increase in demand for power around the world, especially from developing countries in the next 20 years. We're about 3 times. The demand is going to increase by about threefold in sub-Saharan Africa alone. The United Nations estimates that about 3 terawatts of power demand will be seen across regions all over the world. And so if we don't provide clean solutions for this increased demand, we're again really certainly going to exacerbate the climate change issue. So we have a big problem. We have a really big problem in that, and it's sort of the trifecta of these 3 issues where we have increasing global energy demand, we have the need to reduce emissions. And so if you think about that, we're saying we need to build a whole lot more infrastructure, but at the same time, we need to reduce emissions. So if we end up building coal or fossil options, we really exacerbate climate change. So how do we solve these issues with clean energy options? And a lot of folks, would think, well, we have renewables, and certainly renewables are a key part of the solution. And in fact, in the Energy Innovation Center, I believe there are some clean energy firms that either are here or have worked here over the years. And that's a critical part of the solution, but renewables alone can't do it. We really need an all-of-the-above approach. So why nuclear power? I think this slide sort of sums it up. When you look at the energy density that nuclear power has, so a single uranium pellet has the same amount of energy as about 17,000 cubic feet of natural gas. And just to get a better feel for what that is, that's about 17 tanker trailers of natural gas, about 120 gallons of oil, 1 ton of coal. So that's a lot of energy in a very small pellet. So we see in the nuclear industry now this as a huge opportunity. And so we're not, looking at the opportunity to deploy nuclear power plants to solve these big challenges just from an altruistic standpoint. There's actually a huge economic opportunity here. So again, the United Nations estimates about, at least just in Africa alone, about 200 gigawatts of demand. So that's about 1,200 megawatt nuclear plants. That's $1 trillion market in Africa alone. And so there's significant, again, economic opportunities that are going to come for the host countries. Obviously now with this type of energy, they can power their factories, run their industries, but also for the countries that provide the technology. We've estimated that a place like Pittsburgh, that is the home for nuclear power, actually in a lot of senses around the world with Westinghouse, there's potentially 25,000 manufacturing jobs that could be created, and then a lot of other ancillary jobs related to things like regulations, supply chain, etc. So it's a huge opportunity. Again, why nuclear? So we constantly hear in the news around the world of the effects of various natural disasters that occur, and again, even the poor folks in Puerto Rico are still trying to get their energy infrastructure back to pre-hurricane status. So what happens a lot of times is it's not so much the plant, but it's the transmission infrastructure going from the plant to the demand centers. And so we have a challenge to mitigate the effects of climate change. One of the things that the energy industry is trying to do is to make that distribution infrastructure more resilient. And one of the ways to do that is to go with distributed energy versus the typical models where you have a large plant and then you have your transmission lines that take the power all across. So instead of that, we want to have a bunch of smaller plants. And so again, if you think about what we had shown here with the energy density, you can have a lot of very small nuclear plants. Essentially, a plant about the size of this room could power all of Pittsburgh. And just think about that for a second. A plant just the size of this could power all of Pittsburgh and potentially do it without being refueled for 10 years. So it's a huge opportunity. And it's because of the scale. So smaller is better when we think about nuclear. Again, what you see there, it's very versatile in that some of these plants can be put on a barge. So if you think about, when you have these natural disasters, you could put one on a barge and immediately provide power to mitigate the effects of the damaged infrastructure. They could be put on tractor trailers, shipped from a factory to site. And when you think about just how small some of them are, the scale relative to the size of a person, you can really see just how we can really take advantage of this scale opportunity. Still regarding the opportunities that nuclear power provide, it's very versatile in that, you're producing heat, which could be converted to electricity, but that heat also can provide opportunity to produce clean energy through electrolysis of water to provide hydrogen. There's opportunities for ancillary services such as desalination of water. Also, you can create medical isotopes for cancer treatment, etc. It also supports clean energy and renewable options by providing an opportunity to store energy. So one of the challenges, again, with renewables is the intermittency. You don't always have the wind blowing, you don't always have the sun shining, and so you need, for those renewables to be successful, you need energy storage, and nuclear power can provide that opportunity. So if nuclear power is so great, why is it not more ubiquitously deployed, right? So, security, proliferation concerns. Is someone going to potentially access nuclear material and create a dirty bomb, or reprocess and actually create a nuclear bomb? Two very different things. Safety. Anyone heard about Chernobyl, Fukushima, 3 Mile Island? Yes, so those concerns, or just watch The Simpsons, which is actually really the bane of the nuclear industry because a lot of people get their information about nuclear power from how Homer Simpson handles his plant. Sustainability. There's a lot of challenges with the cost of these plants. Also, operations and maintenance, supply chain challenges. The regulatory framework is probably the most highly regulated industry. Also the waste. Everyone asks, well, what do you do about the waste, right? And so the power density that nuclear has, it's a gift and a curse, right? So you have a lot of power, but the problem is that you have a lot of power, right? And so the difference, if you think about how nuclear power is different from every other generation source, is that if you think about coal or diesel or any other type of generation source, what are you trying to do? You're trying to keep it hot. So every day with a coal plant, you have to send in the coal to keep it hot. But with a nuclear plant, you're trying to keep it cool. So once you turn it on, there's a chain reaction that's going to keep on going for thousands of years. And so the challenge is keeping it cool. So it's a very, those three S's, the safety, the security, and the sustainability challenges are really, really big problems. And that's why we don't have nuclear power everywhere. So these companies also solve some very, very big problems. What is it that they do so well? They solve these really big problems with very, very simple solutions, and that's what sets them apart. So if you think about Facebook, it's actually a very difficult problem to say, you know what, that long-lost friend from elementary school, I want to find that person in 5 seconds. You can do that. Facebook allows you to do that. Amazon, I want the best deal that I can get on a product, and I want it in front of my door tomorrow morning. That's actually a very difficult problem. And Amazon makes it possible with a couple of clicks. Google, you want to find out anything about anyone, about anything around the world in a matter of seconds. It's actually a very difficult thing to do. Google makes it very simple. So they create simple solutions to very difficult problems. The challenge that we're thinking about in the nuclear industry is how can the nuclear industry similarly find simple solutions to these very difficult challenges of safety, security, and sustainability. So let's take a step back from nuclear for a while and think about just the challenge of needs in the developing countries and how recently some of these types of big challenges have been addressed. When I grew up in Nigeria, I'd say maybe only about 10% of the people had phones. And it's because of the mess that you see there with the, that was just sort of your typical landline infrastructure. And what they've been able to do is solve this very challenging problem of communications with GSM cell phone technology that allowed you to leapfrog all the challenges that we had with the landlines. And now pretty much everyone in Nigeria has 1, 2, or 3 phones. Actually, not just Nigeria, but all across Africa. So cell phones provided a simple solution to a very difficult problem. And we see just how fast that solution spread across Africa. In about 8 years, you had just a significant exponential growth in cell phone adoption. Way, way, way higher adoption rates than the cell phone companies actually had anticipated. So can we do the same thing with nuclear power, with advanced nuclear power? Can advanced reactors do for power generation what cell phones did for telecommunications? What are the opportunities? What are the challenges? So let's dig into some of these nuclear challenges a little bit more and see how we're finding innovative solutions to tackle the challenges. So again, safety, security, and then under sustainability, there are a whole bunch of items. So for safety, one of the things that we're doing, and I have a couple of slides that explain this a little better, is if you think about any of those accidents that you've heard about, Chernobyl, 3 Mile Island, or Fukushima, essentially there was a failure of a mechanical system. That was a very well-designed mechanical system with very high reliability and expected performance that still failed. So we could go the approach of saying, well, let's make that pump better. Let's add more pumps. Let's come up with some new, let's figure out how we can introduce AI into the cooling system. But what we've done is we actually have made it simpler, and we're looking at how we can achieve the cooling through natural occurring phenomena. So things like gravity. So we're just out of prudence, we're saying that we want to have even a higher level of confidence that we don't want to rely on a machine, we want to rely on nature. And how do we do that? Also for security, they're now looking at how to run these plants for up to 20 years on one fuel cycle. So a lot of the proliferation risks come from the logistics and the movement of the fuel. So most of the existing plants every 18 months have to be refueled. So you take out the old fuel and you bring in new. That provides a risk of proliferation where you could have bad actors access the fuel. But if you have the fuel run for 10 or 20 years, that significantly reduces the risk. In terms of cost, operations, supply chain, regulatory, again, a lot of solutions that are based on the scale. Generally, the smaller the system, the easier it is to manage. So let's explain, let's dig into some of these processes a little bit. Natural convective flow. It's the reason why your basement is cool and the higher floors in your home are warmer, because heat rises. So this simple concept we've adopted in the nuclear industry, and we've been able to design the plants and essentially make them small enough that they can be cooled with this process of natural convective cooling. And generally what we see is that as you make systems smaller, your ability to manage risks associated with those systems goes up. So one analogy that I give with this to sort of understand how we're able to achieve this is, if you think about, say, a really large vehicle like a tractor trailer, because of its size, it has a lot of very complicated systems, including the cooling systems. It has multiple cooling systems. It has multiple braking systems. But then think about a motorcycle. It's small enough that it doesn't have a shrunk down radiator cooling system. It has none. Again, a motorcycle is not a shrunk down version of a large tractor trailer. It's a fundamentally different system that you can actually eliminate systems because of the size. And that's what we've been able to do with microreactors and what we call small modular reactors, where we've made them small enough that we can actually use natural occurring phenomena to achieve some of the critical safety objectives. So we've gone even a little farther, and we've said, okay, what if somehow there's some unanticipated scenario where we are unable to cool the plant successfully, and we do have a loss of coolant accident that then results in radioactive material being released. We've also identified natural occurring phenomena that can keep and trap the radioactive particles in the containment, in the structure. And what you're seeing here is actually, it's just superimposed, but those are images taken in our lab where we're showing that any particles that come out of the reactor can settle close to the reactor. So things like essentially your concern with a nuclear accident is the potential for radioactive material to be released and inhaled or ingested by people. So we're showing that all those radioactive particles are potentially, they're able to settle close to the reactor through natural occurring phenomena. So no fans, no pumps, nothing like that. Again, we're able to show this through processes such as gravity. Also, we're able to show that some of the challenges with cost, we're able to achieve those objectives basically by building more and building smaller plants, because there's this issue of diseconomies of scale that we have with nuclear power plants, where with almost everything else, the bigger you build them, the unit cost goes down. So it's cheaper to build a skyscraper and your cost per square foot would be lower. But with nuclear power plants, it's the opposite that happens because of the complexity and again, the need to add on all these systems for safety. And so what we found is that if you make them small and you build a lot of them, you can actually achieve an nth of a kind cost, which is significantly lower. So one of the things that also I wanted to make sure I communicated is that the end goal is simplicity, but the process and the method to get there is not necessarily simple, right? So what Amazon does in the back office is it's very complicated, but what we see is simple. So I want to show you some of the research from my lab of the processes that we go through to demonstrate that these plants are safe. And so what you're seeing here is my lab in, it's the University of Pittsburgh Advanced Research Center. What you're seeing here is what's called a small modular reactor. It is a 1-to-1 scale, so this is the actual size of the plant. And so we're emulating an accident. There's actually a nuclear accident that's ongoing there. The pressure in there is 200 psi, pounds per square inch, and the temperature is 500 degrees Fahrenheit. It has the actual accident environment, and so we measure the ability of the reactor to self-contain the radioactive particles without any active systems, no fans, no removal systems, and we're able to show that with natural occurring phenomena alone, it was basically safe enough for me to have my iPhone and take that video there. So a lot of work goes into being able to make that simple promise that some of those accidents that we've heard about with the new reactors are just no longer credible. So what are some of the principles of simplicity in a very complex world? Empathy. Again, it's not what we have or what we're trying to sell, it's really what is needed. Scale. Can we go big by going small or by starting small? Also, the concept of that, this is something that architects say a lot, form follows function. Rely on technology or trust technology, and also, when possible, demonstrate the utility in simplicity. I want to take a step back because I want to show how, from nuclear power, and sort of show how this concept can be applied to really anything, right? And so during COVID-19, I was really struck by how it seemed that some very simple solutions were really being complicated. And so if we take this concept of form follows function or, objective focused thinking, and we applied it to the question of whether or not you should wear masks, we would start by understanding that the objective really was to, in a lot of cases, to prevent a virus from entering the body, and that we needed a physical barrier to stop the virus. Then you realize that it's actually not a biological science question, but a physical science question. So my wife is in the audience, she's a doctor, and so we would speak to people and they would ask her, about wearing masks, but they probably should have been asking me because I'm the engineer, because it's actually a physical science question. Once the virus gets into the body, it becomes a biological science question. So I think we had a lot of confusion around just a simple concept about masks, and the fact that any mask, scientifically, even just from some research and modeling that we did, any mask was a good mask. It didn't have to be N95, etc. And also, I think that drove some questionable COVID measures, things like wearing gloves to prevent the spread. I still don't understand how that helped. In some cases, wearing masks in open area, again, the concentration is just so low that you'll never be at risk. But again, I wanted to show how some of this type of thinking could be applied to something that has nothing to do with nuclear power. Empathy. Starting with the end in mind, think about what the customer wants and not what you want or what you are trying to sell. So I think Google achieves this by realizing, and that's why I think they were very successful when they came out with their search engine. It wasn't about what Google wanted. Even though Google wanted to sell ads, and if you look at one of the typical 90s search engine up top there, it was just stressful sometimes just logging into those websites and saying, okay, what did I really come here to do again? And they started not with what you wanted as a user, but what they wanted. They were trying to sell ads, right? They're trying to provide as much clickbait. They're trying to, get you to stay on the website as long as possible. But Google starts with what you want. And then, based on what you want, they're able to figure out how they get what they want, right? So the key there is starting with really the question of empathy and really trying to put yourself in the shoes of the end user. Always start with the objective and not the activity. This concept of objective focused thinking versus activity orientation, it's something a lot of us are guilty of. I struggle with it still every day, and I have to ask myself, am I thinking about the activity, or am I thinking about the objective? An example, this was a school, so a lot of times we think the objective of a school is to teach, or of a teacher is to teach. It's not to teach, it's to ensure that a student is learning. So that's the objective. The activity is teaching. The objective is learning, right? And so, we always have to start, because if you realize that's the objective, then maybe your curriculum that you came in with may not be what's best for that child, and that child learns a different way. So again, starting with learning as the objective and not the activity, which is teaching. Form follows function. Similarly, if you've ever worked with an architect, a lot of them say that, and it's to always think about the end function and then figure out what it's going to look like, right? And not necessarily starting with the design. It's like having a hammer and then looking for a nail, right? So again, focusing on the function and then figuring out what the form needs to look like. Scale. Can you go smaller to make a bigger impact? Should you remove a feature rather than add a feature? There's, I think it's called Restaurant Impossible, where, I don't know, I used to have a TV, we don't have a TV anymore, but I don't know if it's Gordon Ramsay or one of those, or the other guy, okay. And one of the things that he'd always say is, take items off the menu and give your clients, your patrons fewer options. And so, but you might think, oh, well, maybe to sell more, well, let's just put more items so that everyone, finds something that they want. But a lot of times the solution is actually to possibly have fewer options. relying on technology, having technology experts in the room, those solutions that we talked about, Facebook, Amazon, they're very technology intensive. It's important to have a multidisciplinary approach. I'm by no means saying trust the engineers alone. Engineers left alone can be very dangerous. You need a multidisciplinary approach, but it is important to have those folks who understand the technology, and then you need your social scientists, you need other folks who can, ensure that the technology is applicable and usable and simple. Again, remembering that simplicity is the end goal, not the process. The process oftentimes is messy, it's challenging, it's complicated. And because of that, you're going to always have the challenge of people saying, well, it sounds too complicated, it's not going to work, etc., because they are looking at that process to get you to the end goal and not necessarily looking at the end goal. With our cavemen here, similarly, the process of creating that wheel, 1,000,000 years ago would have been very difficult. The end solution is simple, and, that could potentially be why his buddies are not interested. But what he needs to do is demonstrate the simplicity of the solution to overcome potential resistance to challenge. So, in business school, they teach you about, writing a great business plan and getting your financials right, developing a great PowerPoint presentation, and that just bores the heck out of everybody. Whenever you can, leapfrog that and just demonstrate. Again, we know the stories about how folks like Jeff Bezos, Bill Gates, had to speak to thousands of people before they eventually got investors. We know that Steve Jobs was fired from Apple. And so sometimes people just need to see it. So when it's possible, just go ahead and build that app. But also remember that if you're called crazy, if you're called the crazy person because they see you dancing at a distance, then perhaps you just need to invite them closer so they can hear the music and understand why you're dancing.